Hi everyone, welcome to my talk. I'm Niket Agarwal, I'm from NVIDIA, and today I'll talk about our challenges that we face with advanced video curation and how we solve that, and we leverage Ray extensively, so we'll call out where we used it. Here's a brief agenda of the talk today. We'll start off by discussing the scale and the challenges with video data curation. I'll talk about the video curation architecture that we built. And then after curation, also touch upon video understanding and intelligence, which is required to complete the video model training flywheel. So brief introduction for folks who are not familiar with video models. So video foundation models or VFMs is essentially the new LLM. Everyone's trained LLMs or completing training their LLMs. So there are a lot of LLMs out there right now, including open source ones. As we know, text, there's not enough text tokens left to train, right? So whatever number of trillions of tokens that are in the world, 30, 40, people have kind of saturated them. And now most of the companies are working towards multimodal training, which is images and video and audio and things like that, right? However, working on VFMs presents a different scale of challenges that was not faced by text, especially around the data curation aspects, and I'll cover that today. So before I go deep, let's understand what do we mean by data curation. Here I'm showing you the AI life cycle. It starts by taking data, curating it in a manner that we can do training on that data, and then once we train a model, we do inference on that data. NEMO is our framework from NVIDIA to do all the AI life cycle pieces, but there's many open source and other solutions out there, including Scale Ray as well. So what do I mean by labeling training data? Let's start off by an example of what text LLMs do. So most of the text LLMs are next word predictors. So if we want to take training data and feed it into a training model, typically what we do is we give them inputs and then sampled outputs, and the model learns from that. So let's say I'm reading a Wikipedia article and it says the cat sat on the LLM is going to produce the next word, and creating label training data from that is pretty straightforward. You just predict the next word. So curating training data for text is relatively straightforward for LLMs. What you do is you read the sentence and your next word that you read is essentially the next word, label data for that input, right? So there are a lot of solutions that exist for text data, and it's relatively inexpensive to curate because you can just do that on like CPU machines. You don't need large farm of GPUs. Now let's think about what label training data is for video models. And what's a video model? We are going to feed it videos and it's going to understand what it is about, right? So let's say I have just 3 frames of an input video here. Can someone guess what the output for this should be, like the label training data? How would anyone describe these 3 frames? Anyone? Yes. A player is shooting a basketball, right? Yeah, and it could be more descriptive as well. You can say a basketball player is dribbling the ball and then shooting into the hoop. Now remember, we don't know what happened after he shot it, right? So if we had the next frame and we knew whether it's a basket or not, we could add that to the training data as well. But yeah, exactly. This is what creating label data for video models is. Now let's imagine how you would do it for millions and millions of hours of videos, right? So let's say we have a 20-minute YouTube video. Each set of frames, things are changing. Who is going to label this data, right? Humans cannot do it. There's a lot of human annotated data sets out there, but they're in like thousands of hours only, right? There's only so much humans can do. So typically what people have started doing is people have started using AI models to curate data so you can feed it into video foundation model training, right? So we have millions and millions of hours of videos. We actually have AI that watches this video. So in this case, like we watched those 3 frames and we described them. We actually build VLMs, vision language models, that are just good at captioning, right? The stuff that this gentleman just did. And then we feed all the videos into that, and that creates the label training data set out of it, right? Moreover, we don't want to feed junk or garbage to our model to be trained on. So garbage in, garbage out. We want to feed it really high quality data. So let's say we watch like an hour of videos that we found on a YouTube or a movie. Not everything is high quality data, right? Sometimes there's just the same scene. You're watching a tree for 2 minutes. You don't want to feed those 2 minutes into a model. You actually want to filter really high quality data that is useful for a video model to get trained on. This is computationally very challenging, as I will show, and that's the curation pipeline that we have built. So let me start up by a bird's eye view of what a curation pipeline does, and then we'll go into more technical details. At a very high level, what do we do? So NVIDIA has a cloud platform called DGX Cloud. We are actually on top of every cloud. On top of that, what we built is we built Ray data-based streaming pipelines. It's running on thousands of GPUs. I will show why we need them. We are leveraging cloud-native solutions. And then let's walk through what our AI pipeline is doing. So I'll give you an example where, let's say we have a long video, and these are small segments out of that video. So the first segment could be just zooming onto a motorcycle, then someone's driving them under a bridge, and then that person is driving it over a bridge, right? So the first step is we have a set of AIs that goes and finds out which are the semantically relevant frames. So we go and check when frames have shifted the view in the particular video. So in this particular case, the AI will watch this and find out that we have these three frames which are semantically relevant, and they're different than the other frames in the clips, right? So we find these clips, we call them splitting. So we split the long video into smaller clips. We transcode them because we have to feed it to downstream stages, so we want everything to be consistent, and we got these small short clips after that stage. Then we want high quality data, as I said. We don't want things that are, I don't know, PowerPoint presentation is not a great thing to learn from. We want to do motion vector scoring and so on. So as I said, if you have a static tree and a 1 hour video, you don't want to feed all of that to a video model. It's very kind of computationally useless, right? So we run filtering algorithms to find out high quality videos and clips that we should be training on. So we have a bunch of AI models that watch that. And finally, we use a vision language model, as I was saying, and it's trained and expert in captioning short clips, right? So that AI VLM is going to watch this video and then transcribe something like the person is riding a black Harley Davidson fat boy motorcycle on a city street. That's what the model is going to spit out. And finally, what did we get? We got a small set of clips, we got their captions, and we create a data set, then we can feed into a training model to go and train on, right? So it's a very simplistic view of the pipeline, functional view of the pipeline that we have built. All of these stages and models are accelerated on GPUs. We had to do it because of the computational nature of the models we are running, and I'll talk about how we ended up doing that. Okay, so let's zoom in. What does the video processing pipeline look like? I'm highlighting some of the stages. I talked about splitting and transcoding. I talked about quality filtering. There's annotation, which is the VLM part. Then we also do a bunch of things to make the model training data better. I'll talk about them as well. And all of them are GPU accelerated. And finally, we create data sets for training. This entire pipeline has been built to process more than 100 petabyte of data. And after filtering, we reduce it to tens of petabytes. So we throw away a lot of garbage from the videos that we find. So what are some of the challenges in video curation? One is, of course, scale. Training data for text is terabytes, right? Tens of terabytes, hundreds of terabytes. So it's very limited. Videos happens to be much, much larger in scale, way larger than images too. So the data scale is 10 to 100 times of even image training data sets that we find. Dataset orchestration. So like training, which is a distributed training job, our data curation has now become a distributed GPU job itself. It's batch inference running on many, many GPUs together. So orchestrating these AI models and then running them efficiently becomes a challenge. I will talk about in a bit of how we make it efficient. Job failures. For anyone who's worked on large scale GPU infrastructure and processing, jobs fail. You need to restart them. Imagine curating 10 hours of videos, and after like 23 hours, your job crashes. You don't want to start from the beginning. So stuff that people do for large scale training around checkpoint restart, we had to build it in this pipeline because jobs fail, right? We also needed full stack expertise. This is not solving one part of the puzzle. You need to understand how data is stored and in the right format. How do you read it efficiently? How do you orchestrate GPU models? How do you make it efficient and so on? So it's a full stack problem. And hopefully I'll kind of convince you at the end of the talk that, yeah, this is complicated. Okay, so what did we build to solve this? We built a configurable and modular data curation pipeline. Videos come in, and very high quality training data sets come out. what is a trainable data set? Typically, they are clips of MP4s. These are clips that we find. For each clip, typically, you'll either have a text caption, some models need text or video embeddings, so we'll supplement them as well. And this trainable data set goes out from our curation pipeline. Some of the unique things we had to do, and that's why I use the word configurable, is creating curation data curation for video models is actually an iterative process. This is not a solved problem. Every month, every week, there's a new language model for annotation that comes out. And we figured that, we should try it out, we get better caption, and we want to evolve our pipeline. So do you want to redo all those stages that I showed and create a new data set out of it? No, right? We've already figured out after filtering which are good clips. So we just update the captioning model and create a new data set with it. So all of these configurability had to be built into the pipeline, so we're not starting from scratch all the time. Okay? And some statistics, we are curating millions of hours of videos every week for our research models that are being produced, and they're running them on thousands of GPUs. So this is a live pipeline working for months and months, seeing live traffic and scaling. Okay, so then I'll go into, I've kind of talked a lot about why this is complex. Let's go and look at some data. So this is an architectural diagram of the curation pipeline we have built. The way this entire pipeline starts is we start with S3 compliant storage stacks like AWS S3 or GCS. That's where the videos are, petabytes and petabytes of videos. The first step, and again, all of this thing is built on top of array data. So each of these pipelines are a set of array stages. So the first step we do is we take an input set of videos and we let them through splitting and transcoding. So as I was describing, AIs watch the videos and they find small clips that are semantically relevant. We transcode them and then we store them back to storage. Then what do? We found good clips. We run them through a bunch of AI models. So you can see these are again 5 array stages that this video clips will go through. Each of them is a model. So in this particular example, we are running 7 ML models that the videos will go through as part of the same job. Okay? The third step is we find there's a lot of duplicate data, sometimes within a video and a lot of times across videos. So if you have a popular basketball match or a movie trailer or something like that, it's the same set of video all the time. You don't want to over-index on the same amount of data, right? So we do a lot of semantic deduplication as well, and that's also a distributed GPU job. I'll talk about that. Finally, we create these data sets and then upload them back to S3. Note, like you'll see this green box here, which is GPU accelerated. All of these stages, except reading from storage and writing to storage, are end-to-end GPU accelerated. So we use state-of-the-art acceleration algorithms to do that. So I've talked about thousands of GPUs for a lot of time. Let's look at like how we made this pipeline efficient. So when we built this pipeline on day 0 and we did the math, and for a mission we needed roughly 1 million hours of video to go through this pipeline every day. That was kind of the estimation we did to make our research model successful, right? We procured GPUs, we built this pipeline, and we needed around 10,000 GPUs to do this job every day, right? It's a lot of GPUs, as you know, and they don't come easily. So the first thing we did is we found out that we need to accelerate each of the models so they're running most efficiently. It's not enough to just put them on the GPU. As you know, inference is a computationally expensive task, but there's a lot of known ways in which you can make it faster. So we took the baseline. So this chart is showing for our VLM, which was 70% of the pipeline, right? 70% of the runtime was going in that stage because it was very computationally expensive. It's a big LLM that runs inside that VLM. So y-axis is normalized throughput. Baseline is when we started. And then we started doing efficiency on top. So we started with one. We did TRT LLM. This is a known way of accelerating like LLM models. It gave us about 2x throughput. Then we did more memory optimizations to reduce the memory on the same GPU and increase the batch size. We got more speed up. We did FP8 quantization. We did quality studies, and we find it's fine for the quality that we needed. And we are at about 7x speed up of just that model. And it was 70% of the pipeline, so we got 7x speed up reduction of that 70%. We've also done speed of light performance estimations, and speed of light is an NVIDIA term where we used to understand unconstrained what should a particular software speed is on a particular hardware. And it's about 11x. So we know the gaps from today all the way to what it take us to get to speed of light, and we are working on that. Next, so that was one model. So we take each model, accelerate it on the GPU. Now, except AI models, we also do, these are videos, we do a lot of decoding and encoding as part of the pipeline. Every time you want to do processing on a video, it's all compressed, right? H264 other formats. You decompress it. If you do it on the CPU, it's very inefficient. NVIDIA GPUs have hardware encoders and decoders, and we leverage them. So the top part shows our splitting and transcoding pipeline, where the green ones are things that run on the GPU and the white ones are that don't. So we moved all the decode and encoding stages to the GPU and then did the same acceleration on it. And we got 3x speed up of this particular pipeline just by going onto the GPUs, right? So use GPUs for decoding and encoding. And this is the third and interesting thing that you only see when you run what's called like heterogeneous batch inference pipelines. So I'll give you an example. So if you look at the left side of this particular chart, I'm showing a cartoon example of 3 stages. So imagine like splitting, stitching, transcoding, just 3 stages that are running. Each of them is running on 1 GPU each, for example, and they're running at different speeds, meaning the first one can do 4 videos a second, the second one can only do 1 video a second, and the third one can do 2 videos a second. So what ends up happening, even though we build streaming and we use ray streaming, most of the time for the second stage, this GPU is idle because one of the stage cannot feed it data fast enough, right? How do you solve it? Because let's say this is the speed of light, you cannot run it faster on a GPU. You give more GPUs to that second stage and third stage, right? So what we do is we build this auto balancing as part of our pipeline where we measure the throughput of each stage, and then we realize that if some stage needs more GPUs, we run more copies of that stage, right? We spin up more reactors. For people who are familiar with ray, we spin up more reactors for those slow stages, and then finally we get a balanced pipeline, right? So in this example, if we went from 3 GPUs to 7 GPUs, we get 1.7x improvement of the throughput, right? So that's what we get. Okay. So this is example of batch inference and heterogeneous pipelines. This is what we do. Finally, we've gotten about 3.5x speed up over the last few months that we've been working on this, and so our GPU demands have gone down. We have further 2x efficiency that we have found and we are working on, so this requirement will go down even further. 3,000 GPUs is still a lot. So that's the data curation aspect, which is mostly about filtering and then captioning the model so you can train. Just training a model is not enough, or just curating data is not enough to train a foundation model. A lot of things that we need is sometimes domain-specific training. So you might be training, let's say, an avatar model, which has humans who are talking. So you might want to fine-tune the video model on a lot of videos that have people talking, like talk show hosts and things like that. So you need to find videos that are specific to a particular domain. How do you do that, right? Deduplication I talked about. We want to do deduplication. It's not just curation. It's understanding what videos are similar, right? That's a task for AI. And also sometimes we need to debug our models. Now this is very interesting. I'll show an example of how we debug our models as well, and there's other use cases. So let's walk through the rest of the pipeline. So far I've covered dividing long videos into small shots, filtering them, and then captioning them. Let's now go to deduplication. So again, remember, we have billions of clips. How do you dedupe them? It's computationally impossible to do it on billions of clips, all doing semantic search. So first thing we do is to reduce the state space, is we clustered them. So remember, we have video embeddings for each of these videos. We cluster the embeddings using vector search to things that are close to each other, and we form these clusters. So all these videos were there, and then we found basically 6 clusters of videos from the example. This is a cartoon example, okay? And you can squint and see the videos here are similar to each other, right? Then we find videos from them which are semantically identical, right? So the second one and the fifth one you can see is the same gentleman doing the same thing, right? So semantically identical, we don't need to retrain them, so we throw away duplicated data, right? That's how you do semantic deduplication. Again, everything is GPU accelerated. The third thing, which is very interesting, I told you, right? Like you need to find domain-specific data. Sometimes, how do you do it? There's not enough AI sometimes who can do it. So we use manual annotation. So billions of clips is impossible for humans to look at, but thousands of them is. So we create these clusters, and we have humans go and look at some of these centroids manually and then label the data. So all of these things, a human can go and say that, yeah, this particular cluster is good for biking videos, this is for cutting, this is for drone, so on and so forth. We can even mark things as, okay, if you're training a physical world model, then these right side videos are not good at. So this is something we do, and it feeds into the data pipeline. And we have more that I will talk about today. Finally, video understanding. So through this journey of 6 months, what we've realized is you can have great ambitions, you can try to create great data, but the first time you go and query the model that comes out, it's very disappointing. It produces really horrible videos. Okay? So then the journey starts, is okay, I had high expectations, what do I do when the videos aren't good, right? You do all of that, and then you realize it's still not great enough. So let's say we have a video model. We say, make a video of a man dribbling a basketball and scoring a basket, right? Remember I showed you that example? So we ask our generation model to go and create that video. And this is what it's creating, okay? So clearly not a man, but it got rest of the stuff right? So what do you do if you have this video, right? We are puzzled, like, okay, do I look at the parameters, look at the weights, I have billions of clips, what do I do with them, right? So very hard problem. You solve them through video understanding. We want to understand what videos have we trained on, right? So the puzzle we have is, why did the model produce a cat and not a man, right? Very puzzling. Is the model wrong or the data wrong? Let's go and understand that. So first thing is, right, this is an easier example, but let's see if we have videos of man, right, in our data set. We have videos of man playing basketball, right? How do you do that? This is a well-known technique. People are building a lot of RAG pipelines on this. It's called visual search, where you take your videos, you pass it through a video curator, you create video embeddings out of them, and you build a search engine. You pass it the text, it creates the text embedding, and then searches through a vector database. This is all known things that people are doing, but what we did is we stitched it together. So this is a toy example. Hopefully the text is clear. I'll walk you through what's in it. Okay, so we have the database. We'll search for man playing basketball, right? So you can see this is not a great video. So if we all had this, then the model will of course complain, but we have some good videos of men playing basketball. So this is not generation, we are just going and looking at the data set if we have videos like that. If you're interested in other stuff like cats running behind bus, we can go and do that as well, right? So we built like a visual search engine, we'll creates embeddings and searches our database. The other interesting thing is, I'll show you in a second. This tool, because we used a multimodal embedding model, it can also search similar videos. So let's say I have a video, which is this beautiful video, 5-second leaves and raining in the background, and you want to find which are the videos that were similar to this, that led to this. You can go and upload the video to the search engine. It'll create video embeddings and then do semantic search of the videos as well. So yeah, you're going to see quickly, we uploaded, I think. It's now doing embeddings of that video, and you got the data set. So this is input data set, and that was the output of our model. So you can go and kind of understand which videos led to the model that we produced also. Okay? So finally, I think the takeaway from the talk, hopefully it's clear now, this is a hard problem, and you guys need GPUs for it, right? So that is clear from the talk. The things that we did for this curation pipeline was scaling it for a lot of data, optimizing the performance of each of these stages and the end-to-end pipeline, as well as making it resilient and configurable. That's the stuff we had to do for our internal research effort to make our video model successful. And of course, at NVIDIA, we build these technologies so we can help everyone do the same work and more. So if you're facing similar challenges in multimodal training and dataset curation, please reach out to us. A bunch of us are here who are working on this project, so we'll be happy to kind of chat about your problems. Okay, and I have a few minutes for questions. Thank you.
Thank you very much for presentation. So my question is how you tackle the bias in the video generation.
How to tackle the bias?
Yeah.
Yeah, so again, I will pretend that I'm a systems person, right? I'm not an AI person, so I'm going to represent what I have heard from our model people. So the question is, how do you tackle bias? Again, like what I hear from our leading researchers, it's all about data, right? There's a term that our kind of lead researcher Ming Yu uses is data is the ceiling for a model. Most of these models are very similar. Like the papers are out there for LLMs, for diffusion transformers, right? For autoregressive video models. All these papers are out there. Most people are kind of looking at them and building models. Whereas finding the right data to not just train the model, but then fine tune and correct it is the hardest problem. And that's why we have been very hard. So if you ask me how many people at NVIDIA are working on this as part of the video model project versus training the model, it's probably 3:1. More people are working on data curation than training the video model, because this is the hard part, right? So yeah, I think we do it by curating a lot of data, understanding them, and then the researchers can go and debug. If there is bias we see, then we go and kind of figure out why it's happening.
So there are more manual efforts needed than.
Yeah, I think there's, again, this is outside my wheelhouse. There's a lot of guardrails and things like that. So there's standard benchmarks people run to figure out what's happening. The other thing I have heard people do is we show diversity of videos to the model. The more diverse you show, that's where deduplication helps. You're not showing the same thing again and again. That helps the model also get better. Yeah.
Thank you.
Thank you very much. Very interesting talk. I was just curious what your source of data is. Like, where are you getting the videos that you're using for curation?
Great question. It's a very interesting area. So most of them are licensed data. So we take a lot of precaution in making sure the data we get are ethically sourced, legal, and then licensable. So we follow all those practices. So that's what we do.
Yeah, thank you for the talk. So in the beginning, you were, I saw in one of the slides that you had like a FP8 for accuracy. Was there a reason, and can you talk about the accuracy of the, this generation?
Yeah, so I think the question is, can we talk about the FP8 quantization, right? So this is usually a kind of fine balance between performance and the performance people. Sometimes, like the model people use performance as accuracy as well. So the model performance, which is the accuracy, as opposed to the infrastructure performance, which is speed. So luckily for VLMs, there are a lot of standard benchmarks you can use to figure out, because it's been more mature than VFMs, whether the accuracy regressed or not. So we use standard benchmarks to figure out when we went to FP6 to FP8, and you can see we got like 1.5 plus X speed up. So it was clearly worth it. So we ran standard benchmarks to convince ourselves it's still giving us the accuracy we want. And there's new VLMs coming all the time. So we again go with those standard benchmarks to figure out if we should change.
I had two questions actually. One was, do you do this same optimization for every time you're updating your VLM? And you said you're doing this every month. So
sorry, can we speak up? Like you?
Would you be doing this optimization every month whenever a new VLM comes in?
Yeah, so great question. Do we do this optimization every time there's a new VLM? So the great news is this is an industry standard problem. There's a lot of people who are doing inference, and there's infrastructure out there. So you look at this TRT LLM thing. So there's a lot of TRT models out there, a lot of LLM models out there. So NVIDIA has something called TensorRT LLM. It's a framework actually to optimize inference model. So we leverage the frameworks to do it. We don't manually do it. So the way that thing is working is, and if you've heard of NIMS, which is NVIDIA Inference Microservices, what we do is PyTorch model in and an optimized engine out, right? So we have something called a NIM factory. PyTorch models go in, and from the factory something comes out. Now some of the things around memory optimization and other things, for this model we had to manually tune it. We had to kind of do a bunch of things manually, but it's a journey. We want the factory to give us the most efficient model. So we don't redo it ourselves, but yes, we redo it for every model that we get.
The other question that I had is, what has your experience been when you generated the clusters on visual or video embeddings? Did those semantically similar videos actually represent like the same activity or the same semantic meaning?
Yeah, it's a great question. So question is like, how good is our video embedding models, right? So the examples I gave you were from the actual model, right? So it's our internal database. We are talking to it, and they're actual ones. So we did, again, there's standard benchmarks around it. We evaluated a number of them, and we picked the best that's out there. And it's giving us pretty good results. So we're able to debug a lot of these things using our embedding model today. I think there's also a question there at the end, yeah. But after you, yeah.
I know NVIDIA does a lot of simulation work. Is the goal for you guys with this eventually to use a vision model for world simulation?
Yeah.
And what are your thoughts on that generally?
Yeah. So there is, as you can imagine, I'll answer that generically, right? I don't want to talk about product plans, but yeah, NVIDIA does a lot of simulation. We do a lot of graphics. Everything has videos in them, and our hope is this can help all those efforts as well. So we are trying to build models that will help all of those efforts. A lot of them is early research, so depending on how good we get there, it might or might not go into products. Yeah.
Hi, from your ex-colleague. You mentioned that you use radar data. How easy was the sharding to get right? Was it automatically sharded? Did you hit any ooms or imbalances when operating with video? Because very few people have at least shared experiences on it.
Right. So that's a great question. So let me kind of show you this example, right? So the question is like, how good was Ray data sharding, and how much did we have to do it? So we've been using Ray for a couple of years. So we had a lot of maturity right from our image models going to video models. So we didn't start from scratch, right? So the same team developed it. We had to do a lot of things around orchestration for videos because it's petabyte scale. This technique of measuring application level throughput and then spinning up auto balancing of the actors was done at the application layer and not at the Ray layer. And you can imagine that, right? A lot of people do application level load balancing as opposed to like CPU level load balancing is the same analogy, right? You can get, CPUs have this instruction per cycle, right? You can have the same IPC, but way different performance. So a lower level metric cannot capture the application level throughput. So what we found here is measuring the stage throughput in terms of videos per second, right, or video hours per second is more representative. So we built it at the orchestration level because it's application aware. But yeah, if the problem is not this huge, then you can use some of the Ray data auto scaling features, but we had like this huge imbalance. So just to give you an example, and you'll appreciate, if VLM is 70% of the pipeline, then everyone's waiting on VLM, right? Everyone else just has the GPU utilization of 5%, and why the VLM is doing the GPU, right? Yeah. And some of these things actually multi-GPU doesn't help, right? It's because the model fits in a single GPU, a multi-GPU doesn't help. We did try those techniques as well, so yeah. Okay, question here.
I'm just kind of curious around disparate frame rates and how you handle that, and you see trade-offs, performance, throughput.
Yeah, it's a great question. So I think the question is around different frame rates. One of the things we did do, I showed the transcoding stuff. That doesn't take care of frame rates, but it makes sure like we have the consistent format for the downstream pipeline. Some of it we leave it to our training code. So during the training tokenization, we take care of making sure that the model gets consistent, like normalized tokens for it. So we don't do it here, but it's taken care of the training side. Okay.
How is the performance of the embedding search? Like you mentioned, you want to search for using natural language, right? How, like a man playing basketball, like how is the recall or precision of your like embedding-based search?
Yeah, so that example was, by the way, real, right? So it was a recorded video, so I didn't kind of speed it up. So in terms of just, and by the way, that embedding is running on the CPU during the search side. We didn't think because it's not a real-time service, not everyone's using it. So if you meant by system performance, the system performance is very good, right? In terms of precision and things like that, we did off-the-shelf benchmarks as I was talking about, and it's good enough for the things that we are trying to search today. Okay. All right. Thank you.